maybe. So, yesterday, right, we were trying to see some of the just superficially, but some applications how OCT. So, one of course, ophthalmology, which is very established approach. We saw some of those, right, some images of retinal images. We can find out some pathological conditions, etc., using OCT, which is not possible with other techniques so easily. See, we cannot measure or establish what is there right beneath or near the retina, if there is any pathological condition such as macular hole or accumulation of some fluid, etc. It is not easy to find out by other techniques. Okay. But OCT allows us to image layer by layer, and then can help us to determine some of those, right, pathological conditions what we, right, easily by just by using a scanning. We use 800 nanometer light source, 840 nanometer light source. Right, it is possible to use even 940 1064 nanometer light source also, but 840 nanometer light source is used. And now OCT can also be used after 1993-94, when James Fujimoto showed that there are various applications ophthalmology, and they established this system. 1998, Coldstone, they gave other idea about how we can use OCT for intraoral, right, measuring some of the, right, pathological conditions related to intraoral tissues. So, it can be gingival tissue or gum tissues are, right, they are basically taking care of, right, our oral cavity in terms of tooth, as well supporting, indirectly supporting tooth, etc. And at the same time, of course, gingival tissues are soft tissues, and the hard tissues such as enamel, dentine, right, dento-enamel junctions, etc., can also be established using OCT technique. So, we use, let us say, 1300 nanometer light source, and it can penetrate through enamel layer. Okay. Now, enamel layer may be of the order of few hundred micrometers or little larger, okay, and then we can even penetrate through the gingival tissue and capture some of this information. See, this is the pictorial view, while this is the OCT view, and you can see that where there is a refractive index change, characteristics change, that depicts enamel layer, it depicts right, gingival tissue layer, etc. Okay. So, and here you do not require any X-ray source, anything to capture this information, tooth information. You can capture the hard tissue, soft tissues, etc., very easily using this OCT technique. So, now it is also useful for dermatology. So, there was another application in 2000 or so. Of course, this paper is little afterwards 2011, but this is advanced applications, but dermatology is another. So, ophthalmology, dentistry, they started, some research groups started using OCT towards ophthalmology developments, some went to different applications. So, dermatology turned out to be even very useful, particularly for pathological conditions, tissue necrosis, even for cancerous cell detection, reoccurrence of the cancer, right, is also possible to detect using OCT technique. So, so if it is a normal skin tissue, then OCT scan will provide us, right, this type of image, but with some right, pathological conditions such as some structural differences due to some pathological conditions such as carcinoma, etc., we will end up with some structural changes in this scheme, and they can be representing right pathological characteristics. If we do histology, we can also find out this type of tissue characteristics difference, but here in OCT you do not have to remove, right, no biopsy, no histological image is required, you just scan through and estimate the layers right, which are affected due to some pathological conditions. So, this is right dermatology application, and it can be extended even with the help of endoscopy to the right gastroenterology, etc. Recently there is an interest to even go for cardiology application. So, intravascular OCT imaging, right. So, cell lining in a normal artery, and when it is affected due to sclerosis, right, due to the plaque formation within the artery, right, we can determine this aspects using, right, catheter tube with fiber, optical fiber carrying OCT, right, imaging methodology we use to capture the information related to the presence of plaque, etc. Okay. So, this image is I think this is using OCT imaging, and it can determine various layers, etc. Okay. And this may be using ultrasound technique, etc. Okay. So, cathedral tube with a optical fiber, and then it is scanned through, right, it is rotated in order to derive right circumferential information. So, it is right, it is very delicate but interesting application, and lots of research is going on in order to develop this technique in a better way. Can we also use this same technique coupled with a little high power laser to remove this plaque as well, is another approach. So, it is not only diagnostics, but therapeutic application also can be combined with OCT, is also an interesting, right, point. So, that is research. Of course, there are some limitations as far as because if you ablate, and the ablated this particle should be removed quickly, otherwise it should not go elsewhere to trap, right, to get trapped somewhere else. Okay. So, this aspects are important. So, gastroenterology, as I told you, it can also be used along with endoscopy, similar to dermatology, but only thing is it is through endoscopy. Gastroenterology application is also possible. So, you can imagine that the OCT has multiple applications at different right ways, in different ways, and of course, this is just an example. In our laboratory also we had done and estimated what is the enamel layer, etc. We also did some experiments with caries, some small amount of caries within the enamel, which starts forming and becomes a cavity afterwards. So, at an early stage, caries can also be detected using OCT technique. Okay. So, this is the layer OCT image captured the air and enamel, and then the caries was captured here at this point from the top when we did the imaging. Okay. So, this is the way it is possible. Now, one more extension of this OCT is it is also known as of course, it is an extension of OCT technique, but not imaging modalities as such, but to find out absorption, okay, or molecular right presence. Okay. So, it is a low coherence interferometry to detect right, a presence of some molecules. Okay. So, it is, for example, can I capture glucose? Okay. Can I capture some other molecular presence when I am observing in the depth something. So, for example, let us say in a diabetic conditions, generally we use a technique in order to derive the blood sample and estimate the glucose levels. So, there is an interest that non-invasively can we detect presence of diabetic condition or glucose. So, glucose they have various absorption bands, molecular structure, they have various absorption bands, and one band is around 1.69 micrometer or so, 1.7 micrometer, okay, around that absorption band. So, if I use, let us say I use a gingival tissue, because there are lots of blood small capillaries, and that is why you see gingival tissue to be pinkish, this because lots of blood is present in that capillaries. So, use OCT, which is not OCT, but the low coherence interferometry approach, and capture let us say if it is a normal tissue, okay, if it is normal tissue, what we would have observed, okay, I do not have images here, but what we will observe, let us say we will observe with FDOCT the tissue right layers and sub tissue reflections, and right, and so if I try to put it here, right, in terms of right Z, and this is a reference, and then there will be reflection from the surface of the tissue, let us say gingival tissue, and subsurface if there is a right some other layer which will also reflect right light and those reflections. So, or for example, this is the gingival tissue, we will see one this reflection here and the other one over here, okay, right, and this is of course based on the FDOCT, you will see the right image on the other side as well. Okay. Now, in the if I use a source which is matching with the wavelength of absorption wavelength of glucose molecules, what will happen if there is there is no glucose in this gingival tissue, okay, if blood is not having any glucose here, we will see a particular reflection height, right. This anyway will not change, but this will have a particular amplitude or intensity, okay. Now, in arbitrary units of course, but in the presence of glucose molecules, okay, what we will see, there will be some absorption coming into picture, because if this is the wavelength matching with the glucose absorption, due to the right absorption phenomena, this peak right will yeah okay. So, this height will decrease. Why? Because this light undergoes some absorption, isn't it? Intensity will be different at different point of time, okay. So, we can capture this information in terms of presence or absence of glucose, okay. It has up to few tens of milli gram per milliliter, right, or deciliter, milliliter, I think it can capture this information glucose. So, this is based on low coherence interferometry with dual wavelength. Okay. Why we use dual wavelength? Because what we do, we use let us say 1.69 micrometer and let us say 1.5 micrometer wavelength or 1.6 micrometer. So, there is no absorption band, you will observe a particular, right, this image information, and with absorption band you will observe difference, right, and that is indirectly captures the glucose present. Okay. So, it is one more extension of this applications. You combine absorption with OCT or low coherence interferometry and observe the molecular presence as well. Okay. So, this is the way the OCT technique has evolved, and lots of new applications are coming out. Okay. Now, we go to the next topic, right, which is how can we use a laser for or optical sources for therapeutic applications. It is not only sensing, right. So, sensing we understood that we can use maybe absorption techniques, scattering, or maybe scattering means Raman scattering, or sometimes fluorescence, or interferometry approaches, or photoacoustic approaches, etc., for deriving the information, or for monitoring purpose or diagnostics purpose, or for, right, estimating the pathological conditions, etc. However, this optical technique also has applications in terms of therapeutic, right, way. So, therapeutic applications we will try to see in the next. Basically we use electromagnetic wave, of course in the optical range, right, for these there are two important things. Either this interaction of this light source results in a radiative process or non-radiative process. Okay. The radiative processes may be fluorescence, Raman scattering or scattering processes, Brilliant, etc. Acoustic signal, right. So, photoacoustic, right. So, basically they are all, most of this are low power systems, and we basically use it for sensing purpose, right, sensing purpose. While there are non-radiative processes wherein we can achieve photochemical reactions. Okay. So, photochemical reaction may end up with dissociation. Okay. Photon will work, interact with molecules to dissociate them. Okay. Or sometimes if it is a high power laser, if we use, it may end up with vaporization, right, ablation of the tissues, etc. Okay. So, in general, okay, this is right. So, if we talk about photochemical, right, activity, so if we talk about or non-radiative processes, okay, so as I told you, non-radiative processes will be photochemical, which is basically photons interact, photons of certain energy levels, okay, electron volts, okay, certain energy levels interact with the structures and interacts with the chemical, right, bonds, and chemical bonds are dissociated, or altered characteristics such that we end up with right either disintegrating or right changing the characteristics of the right cellular structure or etc. Okay. So, this is non-thermal process, it does not produce any heat as such, non-thermal process, but it is to certain extent it is useful for generating some photochemical activities. We will see examples, okay, how exactly. And the next one is thermal photothermal process. Okay. So, photothermal process wherein photons right with some energy may not be so high to generate photochemical activity, but the energy of the photon may be low, but intensity, the number of photons will be large, intensity is large to produce thermal effect, okay, thermal effect. And so, basically tissue structures, they absorb these photons and via thermal via basically electrons, when they absorb this energy, absorption comes into picture, and then they transfer that energy to the lattice structure, and the lattice structures will transfer through various vibrations through energy to the nearby molecules, and those lattice vibrations end up with thermal effect. Okay. And depending upon the intensity of this photothermal source, light source, the thermal effect can result in maybe heating of the cell or coagulation or melting or vaporization. Okay. It is possible to generate vaporization. Okay. And we can, if we use high intensity short pulse laser, we can induce photoablation. Okay. So, which results in melting and vaporization and plasma formation. Basically removal of material, photoablation, you remove the material, okay, using this. Okay. So, now this photoablation process can be using a laser beam of high intensity laser beam and generating such a right within a very short period of time, few nanoseconds, it will convert the material to the vaporized form or plasma form, okay, ablation. So, that the material will get evaporated, or sometimes the plasma which is generated due to this photoablation will also use to remove the material further. Okay. So, there is this process of ablation can be through direct ablation process using laser source or plasma induced ablation. Okay. So, photons generate a plasma, and then plasma induced material removal will end up with ablation. Okay. So, these processes are basically important for right for therapeutic applications. So, here this is x axis over here is the optical laser exposure time. Okay. It can be a continuous wave laser, it can be a pulsed laser, depending upon the pulse width etc., the intensity will be different, and this is the irradiance, okay, or intensity of this laser pulse. Okay. So, for example, I have a long pulse or a continuous wave laser with a so generally when the pulse width is long or continuous wave laser, the intensity will be of the order of few watts, right, per centimeter square, okay, and it will end up with photobiomodulation. So, what it means we will see it in the next part, but it induces some type of interactions which does not allow material to go to high temperature. It only stimulates those tissues and allows either absorption of this light by ATP or by NO, nitrous oxide in the vascular structures, etc. So that dilation can take place, healing can take place, etc. So, during the some pain, the muscular structure, some particular wavelength of the light can allow biomodulation and allows healing effect, etc. Okay. So, that is photobiomodulation, which is generally low power and continuous wave laser. Okay. And if we go further, where low power laser, continuous, almost continuous wave laser, right, of a few watt per centimeter square, right, over here it induces photochemical reactions. So, what is photochemical reaction? Can be used to form using certain drugs which can generate oxygen, okay, and that oxygen in turn will act as will remove selectively some of the cells. It will act as a toxic this and right, it will remove some of those cells. So, we will see that example as well. The next part is thermal operation for coagulating. So, whenever there is a high amount of let us say if there is a rupture in the vessel and blood is coming out, thermal up to certain extent, if we heat that area using laser selectively and go to 100 degree centigrade or so, it will form a coagulation, okay, and blood gets right clot, blood clot can be formed there in that area. So, that is possible with a slightly higher irradiance power, okay, maybe few hundreds of watt order, okay, per centimeter, watts per centimeter. Okay. If we go with a short pulse laser such as microsecond or nanosecond pulsed laser with a high intensity, we end up with vaporization, ablation. So, removing let us say plaque in the vascular structure or removing stone in kidney stones, etc. This ablation processes are useful, okay. And plasma induced ablation involves short pulse but high intensity laser or ultra short pulse and high intensity lasers. So, we will try to see some of these right approaches in due course. So, of course, this is just parameters which are important from the exposure point of view. So, which wavelength, because absorption depends upon the interaction of photons with the tissue, and absorption is important for the amount of heat which is generated, or I want to go for photochemical reaction or bonding to be disintegrated, I should use high energy photon energy photons, okay. So, shorter wavelength is preferred, but whenever I want to go for thermal effects, I will prefer longer wavelength, right. So, those aspects are wavelength dependent. Power of course is important, as you know, depending upon the power and the intensity irradiance, the thermal effect can be decided, Okay. Then spot size, of course it is related to the area of the laser beam, spatial profile, then irradiation time or pulse duration. Okay. So, in a continuous wave laser, the exposure time, okay, how many minutes, seconds we have exposed that source, or if it is a pulsed laser, what is the short pulse will have higher intensity, longer pulse will have a less intensity, right, laser. Temporal profile to certain extent, and spectral profile, right, of course as a function of wavelength, may not have very large effect, as we may be selecting a particular wavelength as such, and the polarization state also may affect, but mainly wavelength, power, irradiance and duration, pulse duration, right, all these parameters decides how this interaction, right, can be carried forward. Now, I will show you, okay, this we will see, okay, it is not there, okay, anyway. Now, before we go forward, just to give you an idea, already this you to certain extent you know that if I use UV lasers, okay, ultraviolet lasers such as xenon fluoride, which is 355 nanometer, okay, sorry 351, maybe 51 nanometer, okay, xenon chloride 308 nanometer, okay, or krypton fluoride 248 nanometer, or argon fluoride 193 nanometer. All these UV lasers, if we use, which are short pulse lasers, so they allow very small penetration depth. The energy will get absorbed by the very small tissue layer, right, and that will generate the heat, and the heat will be limited within that short within the small region, and it can be used for ophthalmology applications, etc. Okay. So, it can be used to correct the cornea, it can be used to remove cut, right, the corneal surface and go to the lens and correct the lens characteristics, etc. So, this lasers, because their penetration depth is limited and they can still remove small amount of material as well, okay. But they are very high intense laser beam, they can also interact photochemically, okay. They can disrupt the tissue structures as well, in fact. So, particularly a krypton fluoride laser 248 nanometer has the wavelength matching with DNA absorption bands. So, generally 248 nanometer is not preferred, otherwise it can disrupt the DNA activities as well as, okay. So, the laser is detuned to some other wavelength 249 nanometer, slightly detuned, so that absorption can be avoided, okay. So, this, then we go to visible range, okay. Argon fluoride, nowadays it is not used, but instead of argon fluoride laser we use solid state laser, okay. Do you know any of this wavelength which we use in argon fluoride laser? What is the wavelength? 500 nanometer, okay. Hint, it is a green color, 514 nanometer, 488 nanometer. Now, green color light has lots of applications, okay, for our various related to ophthalmology, related to coagulation, bonding, etc. Okay. So, which laser shall we use? We have already discussed. Ruby is 694 nanometer, okay, and Ruby laser is not so efficient. Indiag laser 1064 nanometer, but if you do the frequency doubling 532 nanometer, you will get green color, okay. So, neodymium YAG laser is used, okay. The depth of penetration will be of the order of millimeter order, okay, millimeter order, okay, right, because blood etc. absorption is quite large, tissue scattering is large. So, okay, we go to 650 or 1000 and around that, it is if we go further up to 800 nanometer, then we use titanium sapphire laser. Penetration depth increases by good amount, 3 to 4 millimeter, okay, right, and we can use Nd:YAG laser, fundamental wavelength 1064 nanometer, okay. Here Nd:YAG laser 532 nanometer, correct. Second harmonic SHG, second harmonic 532 nanometer, frequency doubling, okay. So, wavelength will be halved. Non-linearly it can be achieved, okay. We did not go into details of how will we generate 532 from 1064, we just accept it by some process it can generate this, okay. So, that 1064 nanometer here can penetrate up to 3 to 4 nanometers, right, easily, and it also has lots of applications. Short pulse continuous wave lasers are available. Then we also have a laser in 2.9 micrometer range, erbium YAG laser, okay, erbium doped YAG laser, around 2.94 micrometer or 2.7. Water and tissue absorption is quite large, water absorption quite significant, and this use can be used for ablating some of the tissue materials, even tooth, right, ablation etc. is possible using this laser, okay. CO2 laser, which was very much used 10.6 micrometer previously, okay. So, previously before this Nd:YAG lasers etc. came into picture, in 1990s CO2 laser was used to correct the tissue structure whenever there is a retinal pathological conditions, okay. But in order to use CO2 laser, you will have to remove cornea, you will have to remove lens, then only light will propagate through this, okay. Otherwise lens will absorb 10.6 micrometer wavelength light, okay, then it will damage the lens. So, if I want to correct the retina, I had to do such right processes, but now with the help of 1064 nanometer Nd:YAG laser, I do not have to remove any of this, because lens will allow transmission of this wavelength and light can reach up to the retina, and by adjusting the irradiance etc., I can use it for bonding, improvise the bonding. So, that is very important problems with our, in particularly in Indian, many of the Indian this thing, but right, and it is retinal detachment comes into picture, okay. That means retina starts detaching, some of the tissue structures gets disrupted, okay, and detachment means it gets disconnected from the cells, now cells etc. So, you need to bond it back to that thing. Now, how can you do that bonding? So, it is only light to bond. So, basically raise the temperature in that selected area, so that due to heating coagulation and bonding takes place, okay. Not coagulation, but basically bonding takes place because of the thermal effect. So, now that is very much possible with Nd:YAG laser, okay. So, now this operation takes place in, it is not even an operation, it is just a treatment of 5 minutes. Just doctor will ask you to stand in front of the right, this eye surgeon will keep you in front of the laser beam, 3 or 4 pulses and observe through right lens and see, yes, that particular area got affect over, and then next time when you go back, do the OCT scan to see whether the retinal surface has been established. Okay. So, it is a very simple process. In 1990, it will take operation, will remove everything, will bring it back, well, it takes few weeks for something to get cured. Now it is few minutes, and after maybe a day you will be working normally, maybe even half a day, after half a day, okay, or not even half a day, even 1 hour. So, this treatment, what is the time now? What is the time now? 47, okay. So, this treatment allows. So, now this is just a pictorial view that if I use excimer laser, my penetration depth in case of skin tissue, it is stratum corneum, not beyond that. But if I use neodymium YAG laser, I can cross, right, dermis layer and penetrate little more. Okay. So, whenever I want to treat subsurface, right, I would prefer 1064 nanometer light source, isn't it, or around that 800 nanometer 1064 nanometer light source. Okay. 532 nanometer is a green color, that is, it can reach up to sub CS gland. Okay. So, this in general the depth, and right now let us try to see what happens if I am using next class we will go into some of this process, but photobiomodulation is a photochemical effect. Okay. There is not much of thermal effect. Okay. It only allows excitation of the tissue structure to reduce inflammation, healing, etc. So, it is useful during injury and tissue structure has to be healed. 600 nanometer to 1100 nanometer light source or LED is used just to heal the surface. Power requirement is few hundred milliwatts per centimeter square, not very high. Okay. So, it is good enough to excite those tissue structures right through absorption heat, right, but not through thermal effect, but light gets absorbed, it chemically induces chemical, right, activities in terms of dissociating bonds or etc. little bit in terms of photochemical activity, so that the tissue gets excited. The photochemical effect further, right, large with a high power, little high power, right, laser with a little pulsed laser can induce photochemical effect, and it is useful for photodynamic therapy to remove selectively some of the cells in the region. Let us say there are some cancerous cells, we can induce some drug which can attach with the cancerous cell, and this laser, red laser will interact with those cells to produce certain chemicals, and they in turn disintegrate those cell structures. Okay. And subsequent to this is the thermal effect, which is depending upon temperature, it can be coagulation, it can be vaporization, okay, it can be ablation, okay, to remove the layer. Okay. If I want to remove the cornea structure something, I can use that. I can remove kidney stones, I can remove plaques, etc. Okay. And plasma induced, it is basically dental applications, ophthalmology applications, etc. it is useful. So, we will try to see some of these methods, what exactly they do in terms of understanding the mechanism, and then application little bit in the next class. Okay. So, with this. I stop here.